Hello, I'm Nathaniel and today we are now doing A-level mathematics. This is the last topic of Peer 1 which has 10 chapters. This last chapter we're going to do is called the differentiation. And you haven't seen why I haven't done chapter 10 yet, but actually I have, and it's just after the differentiation video chapter 8. A reason for this strange ordering is explained in the video about integration. How about that? Okay. Just letting you know, the textbook I'm using is by Linsky, Nicholson and Weston and is made by the Oxford University Press. Let's talk about the uses of differentiation because that's what differentiation is for. And you know, differentiation is about gradient, not anything else. It's about gradient, slope, tangent. So one of its most natural uses is for increasing and decreasing functions. So when the dy over dx is greater than 0, it means increasing. It makes sense because in dy over dx is 0, it just be a straight line, and when it's greater than 0, it will tilt this way, and when it's less than 0, it's decreasing, so it would tilt the other way. Now, do you understand why? Now let's talk about stationary points. Surprisingly, the derivative is extremely useful, and you can also use it to find stationary points, which encompass maxima and minima. And these occur when dy over dx equals to 0. So you go look at this table. This makes sense because when you do it this way, with less than 0, then greater than 0, it's a minimum. And when you go greater than 0 and less than 0, it becomes a maximum. Now, do you understand the rationale? So dy over dx is actually a very natural measure for finding stationary points. Now, why would you need stationary points? Just why? Well, we need it for optimization. So say you're in the stock market or a cardboard box maker, whether you're in any profession, you might most certainly need calculus and you need any problems with change or optimization. And it's all about the extremes. These extremes are the minima and the maxima of the function. Now, there's a really good example in the textbook. But remember, always check for extreme values. Minima, maxima, whatever. So, besides, you will also need to substitute some values to check in your minima and maxima are around that figure. A good range to start is by minus 0.001 and plus 0.001 to check you're on the right track. And it's consistently increasing or decreasing, and that means you need to check your values again. See how I'm dispensing wisdom about trying to check your answers in your exam? Now, this is the really good example from the textbook. A closed box with a square base has a total surface area of 36 m squared. So, you're right, it's actually a cuboid with side x and height h. So, always draw a diagram and use letters for the left-hand sides. You can use any letters, but if it isn't clear what your letters mean, then the examiner will basically minus all your marks, okay? So Cambridge is really simple about this. So and you don't state what your variables mean unless they're standard variables, then they'll minus your marks. How about that? So here's the solution. First, we need to find the volume, x squared h, and the surface area equals to 36. Then we solve the equation to find h in terms of x. Then we find v, we substitute h inside, and then we get v. And then we do dv over dx, which is basically the change of volume with respect to x. So why are we doing this? It's because we need to find the maximum volume, not the maximum height. Got that? That's why we chose dv over dx, not dh over dx. So 18 equals to 3x squared. X squared equals to 6 and x equals to plus minus the square root of 6. However, x is a length. See what I mean about cardboard box makers? They always need to use calculus. So the volume, 9 times square root of 6 minus half times square root of 6 cubed equals to 6 root 6 meter cubed. There. That is our maximum volume. And if you try it for other values of h, you will get a volume which is less. This makes sense because when you have a large but flat box, the volume will be small. And then you have a tall but thin box, the volume will also be small. So there is this happy medium where the height is actually equal to x and so forms a cube. Now, do you understand why we need calculus for even cardboard box making? So, this brings us to an end of Pure 1. But don't stop yet, because I'm going to talk through two more applications of differentiation to find stationary points and to find limits. Stationary points, well, second derivatives give us a method to find stationary points. So second derivatives are what you expect. It's a derivative of the derivative. And like I said, they need to find stationary points. But this time, the second derivative table is much, much easier than that on the first derivative table. And also, second derivatives can also be used to test concavity. So second derivative is greater than 0, it's a minimum, and it is concave up. When it's less than 0, it's a maximum, and it's concave down. That is what we learned in university mathematics. We use the second derivative to measure concavity and find stationary points. What about Lhopitals Rule? This is a very slick rule, and you see why it's slick for finding limits. So this is Lhopitals Rule. Can't you see why it is slick? Because we just put primes on the functions and we're done. And this limit will only work when f of x over g of x equals to 0 over 0 or infinity over infinity, meaning that it is indeterminate. Now that I talked through about these already, as I wave goodbye to all of you, see you! And this also means in chemistry speak, copper! Don't forget to say zinc to me when I come back.